It's also the z, y, x Euler angles. Okay, which means we will first rotate about z-axis by an angle psi, then we'll rotate by theta about y-axis, and then phi about x-axis. So how does that go? So this is the topic we'll be discussing in the first half. So how does this go? Well, first let me show the coordinate frame. So x, y, and z. Next, I would rotate about the z-axis by an angle of psi. So if I do that, and that rotation is always counterclockwise, as if you take your right hand and you turn your finger, if your thumb should be along the z-axis, then the curled fingers gives you the direction of the rotation, which is this way. So when you do that, and you do that by an angle of psi, what you would get is the new y would be like this, the new x would be here, and this angle here is psi. Okay, that's rotation 1. Now let's rotate about the y-axis by an angle theta. So what I'll do is I'll redraw the axis in the rotated frame, which means that I'll draw keep z as it is, draw the new y, so let's call that's y prime, and then we have x prime, and then z is unchanged because we had rotated about z. So the next rotation is, and I'll show it in red again, is about the y-axis by an angle theta. So again, what I do is I need to curl my finger along the direction which corresponds to positive. That happens when my thumb is pointing along the positive y prime direction. So when I do this, and this is slightly hard to imagine what's going on here because of showing this in 2 dimension, but it will be something like this. So the z would shift, and I'm going to call that z double prime because this is my second rotation, and then x double prime, and this angle here are going to be theta and theta. Okay, so that's my second rotation. The third rotation is about the x-axis. So let me redraw, let's say in green, the old axis here. The old axis would be y prime, that's unchanged, and then z is changed to z double prime, and then x is changed to x double prime. So that's my original axis, and now I'm going to rotate by an angle of phi along the x-axis. So again, I do the same thing. I curl my fingers along the positive direction such that my thumb points along positive x prime axis. So if I do that, then what will happen is the y prime will rotate to y triple prime, and then z triple prime. So that would be phi and phi. And so that's my final configuration. Okay, so if you take an object and you do this, you can, if you want to visualize this, you just do it by say 90 degrees. It's much easier to visualize, but that's what's going on. So the axes keep changing, and as I've shown you in the past, these axes are local axes. They rotate as the body rotates. So the z-axis will always be pointing along the direction in which I started along. But in the global frame, on the fixed frame, like I've shown it here, those will change to prime and double prime and triple prime. Okay, so we have these three rotations. How do we actually compose these rotations, or how do we represent these rotations using the rotation matrices I talked earlier. So this is how you do it. Okay, so let's assume we had a vector in, so let's call this, let's say this is the vector is C0 here, okay? Then it undergoes rotation and becomes C1. And then finally it goes, rotation goes to C2, right? This is similar to what we had seen for the manipulator. We had axis O, XO, YO, O1, X1, Y1, and then we had the unit vector in frames 0, 1, and so on. Similarly, these are vectors in the individual frames. Okay, so we had a vector in X, Y, Z, and that we called C0. Then we have the vector in X, Y, X prime, Y prime, Z. Since only the X and Y change because we have rotation about Z, so Z doesn't change, and that would be, let's call that C1. And then we have X double prime, hold on, I did an error. So this is my bad. So C0, I should write it this way. C0 becomes C1. It's probably the best way to write it. Right? C0 is the configuration in the original frame, and then 1 is for the prime frame. And then C1 becomes C2, and then C2 becomes C3. So this is perhaps a better way of writing it down. Okay, so then we have X prime, X double prime, Y prime, Z double prime, and then we have C2, which is in X double prime, Y triple prime, and Z triple prime. Okay, and then finally we end up with C3. So the way we do this is C0 is related to C1, okay, by a rotation matrix, and that rotation matrix is rotation about Z axis, because the first rotation here, if you see, was along the Z axis. So that rotation is psi about the Z axis. Next, we rotate this vector C1, okay, to get C2. So what I need to do is write C1 equals C2 with, there's a rotation matrix missing, and that rotation matrix is rotate about the Y axis. So I'll write R, Y, theta. And then finally C2 equals a rotation matrix, which will be X, rotation angle is phi, and so Rx phi times C3. So if I do the math here, which is essentially substitute this C1 there, and this put this C2 there, then I end up getting C0 equals RZ psi okay, RZ psi RY theta Rx phi times C3. So what it's saying is that if I want to consider the effect of 3 rotations, and I need 3 rotations, remember, to describe in general 3D rotations in space, then the rotation matrix, which helps me to transform from that orientation, the final orientation, which is this, to the orientation in fixed frame, is this rotation matrix. So in other words, I could write C equals R times C3, and R is the rotation matrix I'm trying to seek, which tells me how the object could be oriented from the final configuration C3 to its configuration in the fixed frame, the frame which does not move. So that R is now Rz psi Ry theta Rx phi. And I written down expressions for these three rotation matrices. So what you can do is you can, well, first of all, let me write this. So R equals R times R P. Okay, so this is the general formula I derived, where RB is the position in body frame. Okay, or the fine, it's basically the, or if you remember, it was, if you looked at the two link manipulator, the position of this point, so let's call this x1, x0, and x2. So if you wanted the position of this point, which is Q, then its position is L along x2 and 0 along y, right? Because the y-axis are pointing in the normal direction. So this is the position in body frame. Okay, so if you have the position body frame, then we can find its position in the fixed or the world frame by using this transformation. So R here is the necessary rotation matrix. What you could do is you can try to find what that R is, which essentially means you need to take the rotation matrices, those 3 by 3 matrices I wrote down earlier, and then do the multiplication. And that is kind of tedious. And so what I did was I actually went in MATLAB and made MATLAB compute this rotation matrix. It comes out something like this. So R is again R, Z, psi, R, Y, theta, R, X, phi. And when you expand this, you get cosine of psi, cosine of theta, sometimes it's just easier if I just do it this way. So it's easier to see, it's easier on the eye. So let me just do it. Just draw the red lines to make it easy to see the columns and rows. Sine, psi, then minus sine theta. So that's the first column. Next we have cosine psi, sine phi, sine theta, minus cosine phi, sine psi, and then cosine psi, cosine phi, plus sine phi, sine psi, sine theta, and then cosine theta, sine phi. This is probably the only time I'll write this down, because you never really do this math by hand. You always use a computation, a symbolic computational package to do this. So sine phi, sine psi, plus cosine phi, cosine psi, sine theta, then cosine phi, sine psi, sine theta, minus cosine psi, sine phi, and then finally cosine phi, cosine theta. So it's just a mess, but then you never really worry too much about it. Okay, so that's the R, and you shouldn't have to do it. You should only have to do it symbolically or numerically when you have to do it in MATLAB. So when I showed you those animations, yes, last class on 3D rotations, I was actually doing this kind of rotation matrices. I was multiplying the rotation matrices in a specific order to get the net rotation. So if it was y followed by x, it would be ry times rx. That's what I did first time. And then when I showed you the opposite rotation, I did rx times ry, just reversed, and you got the new rotation matrix. Okay, so that is the 3, 2, 1 Euler angles. Okay, all you need to know about it. Any questions on this? Okay, so let's now get to the next thing, which is velocities in three dimensions. So 3t angular velocity. Okay, so in 2D, we've shown that, well, first of all, what's rotation in 2D? In 2D, it's basically x, y. If you remember, we rotated the frame to x1, y1, and then this was theta, right? And what was really going on was, and I just showed this to you in the three-dimensional picture, when we did this rotation, we were actually rotating about the z-axis, right? So if you curl your finger, you point a thumb along z-axis, the positive z-axis, and your fingers will actually turn the direction of theta. So the angular speed was omega z. So I'm going to use vector notation. I've not introduced it in the class, but I'm assuming that you uh, would remember. Actually, I'll do a little bit of vectors a little bit later today. So omega z is a vector. The way you show a vector is by an arrow, equals theta dot times k. So what's omega? The line this means it's a vector. The vector k is a unit vector along z-axis. So that's just saying that the angular speed along z-axis is theta dot k, and this is the picture which goes with it. Okay, so that's nice. Now we also have in 2D, if you want to find the velocity of a point, then that's omega crossed with r. What does that mean? Well, if you have a rigid body and if you have a point P, let's call it P, and if you want to find its velocity, that is the linear velocity, when it's rotating or spinning by an angular speed omega, and if this is the vector r, which basically gives the distance of the origin from point P, then the velocity is always given by the cross product. This is the cross product. Okay, what does the cross product do? Well, if you write omega as omega 1 I plus omega 2 j plus omega 3 k, and then if you write r as r1 I plus r2 j plus r3 k. Okay, so what's I, j, k? I did use k, but I, j, k are unit vectors along x, y, z axis. So they point in the positive x, y, and z axis, but they have unit magnitude. Okay, so this is how you would write a vector in three-dimensional space. It has a magnitude of omega 1 along the x-axis, magnitude omega 2 along the y, and magnitude of omega 3 on z. Similarly for the positions. So if you want to do vp cross vp, which is omega cross r, if you want to do this in MATLAB, you simply say cross, you say v equals cross omega and r, where you define omega as a vector. That's the way you'll do it in MATLAB. Okay, if you want to do it by hand, and this is something you might remember from an earlier class, what you do is you find the determinant of this particular form, right? I wrote ijk for the unit vectors. I wrote omega 1, omega 2, omega 3 for the first vector, and then r1, r2, r3, and that comes out to be, okay, so you could also use this form also can be multiplied in MATLAB using determinant, but the way you'll do it by hand is you'll take I and then multiply omega 2 with r3, then omega 3 r2 minus j. So don't worry if this was intimidating, but you will not have to use this. I'll just use this because I need it for a derivation later on. Okay, so that's okay. So looks like I did an error. Omega 2 r3, that's right. Omega 2 r3 integrals. Yes, perfect. Thanks. Okay, so that's VP. Okay, so that's how you write the velocity using vectors. Now, so I showed you two things. One is that fact. Let's call that, let's say that fact 1. And then the other fact I said was this, fact 2. Okay, one of them tells you about angular speed only, and the other one tells you about the linear speed. So angular, and this is linear, angular speed, and then linear speed. Okay, so the good news is that this formula, which I wrote down in 2D, is actually valid in 3D. So you just write the same thing in 3 dimension and it's nice. However, this fact about the angular speed, which is true in 2D, that is omega z equals theta dot k, doesn't quite translate to 3 dimension, and that's where all the that's why it makes 3D rotations quite hard. So remember I talked about rotations in 2D to 3D. You can't just take the rotations about x, y, and z axis and just add them like theta 1, theta, phi, and z. We had to go through that rotation matrix. Similarly, when you do the rotation angular speed, you have to go through the rotation matrices to do this. So let me write that down here before we proceed. So fact 1 does not work in 3D. That is, if I were to write omega, I cannot write this is theta dot. See, I had the phi, right? Phi along x-axis, and then I had theta along y-axis, and I had psi along k-axis. So let me write that dot 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 for the angular speed. You would think that's true. That's simply not true. This is not correct. However, the fact 2 does work in 3D. In other words, if you write the velocity of any point, that's omega cross r. Okay, so we do not know what omega is in 3D because that formula doesn't quite translate to 3D, but we do know that the velocity formula does translate. Okay, so the second half of today's class, I'm going to try to show you how to derive an expression for this, how to get omega in 3D. Okay, and that's kind of central to this topic because once you know the angular speed, you can then find the energy, and once you know the energy, you can find the equations of motion, and once you know the equations of motion, you can do control. We've not talked so much about control, but you can use those equations to control. So we'll go to videos and come back to this, and I'll start showing you how to find the angular speed in 3 dimensions. Any questions on anything so far? So today's class is going to be a lot of math. What's that? So let's denote that by S, okay? And then if we have S, and the way I'll show this is S of A. Okay, why A is because okay, the question, how will this robots deal with fence obstacles? Well, I don't know. Well, if you the biped could have hands, the drone doesn't require a fence, but I guess there are ways to go around it. Maybe they will only deliver when you are at home, so you will open the fence. We'll see. We'll see how it goes. Throw the package. Wow. Okay. Okay. So S of A is 0 minus AZ AY AZ0 A, sorry, minus AX, then minus AY AX 0. So what's AX AY AZ? So A is imagine A is a vector, AX AY AZ. So it's a 1 by 3 vector. It could be the angular speed in 3 dimensions, right? Omega x, omega y, omega z, or it could be position rx, ry, rz. So it's just any vector. So if you want to write the skew symmetric matrix associated with the vector, this is the form. Okay, so this is the definition of a skew symmetric matrix. Now here's a property of skew symmetric matrix which you can check. If you do S of A plus S transpose of A, okay, so if you take this matrix and you take the transpose and sum them up, you should end up with zeros. So this is one property. The second property, which is see, so if you have a matrix, if you have a cross product A cross B, okay, where A is a vector and B is a vector, then it turns out that you can write this as S of A times B. It's kind of a neat thing because on the left side you have a cross product. So this is vectors, right? One vector times another vector. Here you have a matrix which is then multiplied with a vector. The claim here is that if you do this in this fashion, A cross B, then you will end up doing a matrix multiplication of the vector, which is actually a nice thing because most of things we do in this course are actually about, in 3D especially, are about cross products, but we are allowed to replace a cross product with a matrix. And once we can do that, we can do math with a matrix, it's so easy to put that in MATLAB, which is because MATLAB is entirely, the whole system is based on matrix manipulation. So I will actually show you how this works because I think it's an important property. And the third property, which I'm not going to prove, is that if you have R times S of A times R transpose, then you can actually write it as S of R of A times B, okay, where R is the rotation matrix. Okay, this is only true if R is the rotation matrix. If you take a random matrix in place of R, this does not work true. So it's only works if R is a rotation matrix. So the proof is in Spong's book. So there's a book I reference. The proof is actually in that book, and so that's one way to look through the book and see the proof. But the other way to do this is to actually assume some rotation matrix, right? We've seen rotation about X, Y, and Z. S, you can take the generic form AX, the one which I wrote down here, and just do the multiplication yourself and see if this works out right. Yes, you can just do it by, so that's one way to check this. The other way to check this is to do this calculation for a specific R matrix. Okay, so what I'm going to do is I'm going to actually not show you 3, but I'm going to try to show you two, which I think is very important. And a lot of things we'll be doing today are going to be based on number two. Okay, so proof of number two. So we will show this. Okay, or we will prove this. And we'll prove it just by brute force calculation. So we have A cross B, and I wrote down the formula for A cross B. That's right. It's I J K. We have A X, A Y, A Z, B X, B Y, B Z. So this is basically taking the determinant of a 3 by 3 matrix. And if you check that, it comes out to be, you first take the ith element and then you multiply AY with BZ, then AZ with BY, minus J, then we have AX with BZ minus AZ with BX, and finally K that will be AX BY minus AY BX. Okay, and so another way of writing the same thing down is, this is the I components. That's going to be the first element, AY BZ minus AZ BY. This is the second component, but remember there's a minus sign. So what I'm going to do is move the minus sign inside, and so this term, second term, is positive. So AZ BX minus AX BZ, and then finally we have AX BY minus AY BX. So this is what A cross B is, because after all, what we have here is the X component, the Y component, and the J component. So the I, the J, and the K, or the X, Y, the Z component. Okay, so now let's do the same thing with S of A with B. So that is, remember I wrote the form for S, that's 0 minus A Z AY AZ 0 minus AX minus AY plus AX and 0. And then B is simply BX BY BZ. So we need to do this matrix multiplication, and that comes out to be minus AZ with BY plus AY with BZ. Then we have the second row with the column, so A Z BX, then minus AX with BZ, and then we have minus AY with BX, and then plus AX with BY. Okay, so we need to check if, let's call this 1 and let's call this 2. And so we need to check it element by element. So we have AYBZ, which is right here, minus AZBY, that's right here. So it checks out. Next, let's look at the next term. AZBX, that's here. And then AXBZ with the negative, that's right here. And then finally, we have AXBY, which is right here with the positive sign, and minus AYBX, which is right here. So 1 checks with 2, and so we can say that 1 is equal to 2, and so we say that A cross B is the skew symmetric matrix associated with A times B. That's true. This checks out.